Hello everyone, this is my video overview for MBAI5310G Assignment 1 and Question 1, which is using the Abalone dataset from UC Irvine. So I started by downloading the dataset from UC Irvine using the provided link, and I loaded in pandas to read. But since the file doesn't include a header row, we have to define a list of names for the columns before loading the dataset into the data frame, which is what this line is here for. So I added all the column names that correspond with the data, which included the sex, length, diameter, height, whole weight, shucked weight, viscera weight, shell weight, and rings. And then I created the data frame named Abalone, read CSV method in pandas. But before we can split this to convert these columns into numbers, which we use encoding for. And this part I referenced and followed examples from our textbook, Garon Chapter 2, Handling Text and Categorical Attributes. So since the sex column contains the text values of M for male, F for female, and I for infant, we have to change them into numbers since neural networks only use numbers. So this line of code will convert the MFIs into numeric code such as 0, 1, and 2 using the ordinal encoder. So now we can split the data into training and validation sets. So this line divides the data into equal parts, 50-50, where the first half is used to teach the model and the second half is used to validate how well the model learned. So this part I referenced and followed examples from Garon, also Chapter 2, in the section titled Create a Test Set, and we use the train test split method, which is over here. So we set the 4 different parts of the set, where ABX is the input, where the target would be the sex. So we removed that target from the rest of the measurements, and then made ABY the answer, which is just the sex, specifically the encoded sex from the previous line, to make sure it runs correctly in the network. So here we can run the code and it will split the data into half, which is here where the test size is 0.5, 50-50. And we'll move on to part B of the question, which is to train a core model using Curious Model Sequential that will classify abalones into male, female, or infants with the intention to overfit the training data. So we install TensorFlow and import the following libraries as well. So to create the model using the sequential API, I referenced and followed examples from Garon Chapter 10, the section for implementing MLPs with Keras. So we started with setting the random seed to ensure the same data split is being used each time, then initialize the model and set the input layer to 8, which is the number of measurements in the data set. Then we added in 2 large hidden layers with 2048 and 1024 neurons each. Specifically, we made these larger layers to increase the capacity of the model to push it towards overfitting the data and where it starts to memorize in training set. Then we added in the last output layer of 3 neurons, since there are 3 possible categories: male, female, and infant. The softmax activation takes the output numbers from the network and then converts into probabilities that add up to 1 or 100%. Something that males are 10%, females are 20%, infants are 70%, which would add up to 100% of the data set. So this just makes it easier to see which is the larger value or category. So then after we use the .compile method to set up the learning rules, we set the optimizer to SGD, which is the stochastic gradient descent, classic method model, and is usually slower than other optimizers. So SGD can sometimes lead to a model that generalizes and paired with a learning rate of 0.1, which we can see over here. It controls the model as it trains. So we use SGD just to use a more traditional optimization approach. And then in part C, we do use Atom for our tuned model just to make it a more adaptive optimizer that adjusts the learning rate automatically. And this usually leads to better results with less tuning. So we also here for our overfitted model, we set the loss to cross entropy, which is to calculate the error for categories, and metrics to accuracy to track how often the model is right. So then next we also use the dot fit method to train for 100 epochs and set the process to history B, just so that we can plot the graph in the next part. So here we'll watch as the model runs. Okay, so from here we can see that the model has completed its training. So now we can move on to the next part where we use pandas to plot a graph that depicts the loss accuracy, validation loss, and validation accuracy. I referenced the creation of this graph and I followed a sample from Garon chapter 10, section for training and evaluating the model, specifically based on figure 1011. So from here, this creates a graph of the model's layers, and we can see that the training and validation errors are diverging to create a large gap, which is a clear sign of overfitting. So the gap shows the model mastering the data but failing the test when new data is introduced, and it's a sign that it stopped learning patterns and has begun memorizing specific rows. So the training accuracy line hits nearly 100%, while the validation accuracy stays much lower. So this gap opening up on the graphs are an immediate sign of overfitting. So these ones here. And was built with layers of 2048 and 1024 neurons. The model had a lot of space to memorize the data instead of learning patterns. And to improve the model, we started part C to change some of the hyperparameters in the model we created, which is over here. So here we were using Curious Tuner and created a new model with some of the same base layers of the previous model. So this model, which is model C, had the same initial setup of 8 inputs, which are the 8 physical measurements of the abalone. And then we added 2 layers of 64 neurons each to create a simpler model to learn the patterns instead of memorizing and prevent the issue of potentially overfitting again. And then the last layer of 3 neurons is the same as the previous model, which is 3 for the 3 categories, male, female, and infant. And we also use softmax here to get the probability scores. So to compile the model, we use similar parameters, but this time we change the optimizer to Atom. and a learning rate of 0.01. This is a more common setup where Adam can automatically adjust the learning speed for each parameter to make things faster. And this model also trains for 100 epochs. And then we also created a graph similar to the last one. And we can see that this model is training. So after it's completed, we can move on to the graph here. We also set in an early callback for an early stop, which stops at around 20 epochs, just so that it prevents overfitting as well. So going into the graph, we can see that the model here, the validation and training lines stay a lot closer together, and it does not approach any signs of overfitting like previous, which is a much better model than the first one. And then finally, in part D, we are displaying each model using the Keras Utils plot model. And this I referenced and followed examples from the TensorFlow's official site and library to set the section up. And we plotted both model B and model C. Okay, thank you.